Hello good people, I'm going to talk about stoichiometry and the mole. Recall that a single mole represents the quantity of 6.022 times 10 to the 23rd. This number is also known as Avogadro's number. How does this relate to stoichiometry? Let me bring in a balanced chemical reaction equation. Here we have one formula unit of magnesium chloride reacting with two formula units of potassium hydroxide to give one formula unit of magnesium hydroxide and two formula units of potassium chloride. Magnesium hydroxide is the active ingredient of milk of magnesia, and it is often used to treat heartburn or to help with digestion. It is a very potent laxative. Suppose that I want to end up with a dozen magnesium hydroxide formula units. How much magnesium chloride and how much potassium hydroxide would I require? The word dozen stands for 12, so I'm going to write it in front of the formula unit for magnesium hydroxide. Comparing the original chemical reaction equation to the one that I'm setting up right now, I have increased the amount of magnesium hydroxide 12-fold. Recall that chemical reaction equations represent directly proportional ratios. Whatever happens to one component needs to happen to the others. I have increased magnesium hydroxide 12 times. Therefore, that is what needs to happen to my reactants as well. And now I could say to get a dozen of magnesium hydroxides, I would require a dozen of magnesium chlorides, 2 dozen of potassium hydroxides, and I would also end up with 2 dozen of potassium chlorides as a byproduct. I cannot actually measure out 12 magnesium chlorides. However, I can measure out a mole of them. Here is the reaction equation again. And this time I'm going to say that I want 6.022 times 10 to the 23 magnesium hydroxides. What amount of reactants will I need? Based on the original reaction equation, I have multiplied the amount of magnesium hydroxides by the Avogadro's number. And because this is a directly proportional ratio situation, whatever happens to one component needs to happen to the others as well. And so I will need 6.022 times 10 to the 23 of magnesium chlorides. How many formula units of potassium hydroxide will be required? Well, the ratio between magnesium chloride and potassium hydroxide is 1:2. So for every magnesium chloride, I will need 2 potassium hydroxides. In other words, the 2 needs to be multiplied by Avogadro's number. And that would give me 1.2044 times 10 to the 24th. The same is true for potassium chlorides. As you may have noticed, Avogadro's number is a little bit cumbersome. So rather than saying I need 6.022 times 10 to the 23 magnesium chlorides and 1.2044 times 10 to the 24 potassium hydroxides, in chemistry we would simply say that I require 1 mole of magnesium chloride and 2 moles of potassium hydroxide. And so the reaction equation might be written something like this. 1 mole of magnesium chloride, and recall we do not write the 1 in, plus 2 moles of potassium hydroxide will give me 1 mole of magnesium hydroxide and 2 moles of potassium chloride. The more observant of you might say, aren't these the very same numbers that we've started in the first equation? Absolutely. When we write a balanced chemical reaction equation, we could be talking about molecules, formula units, and atoms, or we could be talking about actual moles. In most cases, we are talking about the moles. And that is simply because moles are something that we can deal with on a macro scale. It is something that we can measure out in a lab. This means that when we talk about a stoichiometric ratio, we are also talking about a molar ratio. Now you might be wondering, how did we settle on this rather awkward number representing a mole? This has to do with the mass of elements. In fact, the word mole comes from Latin and it means mass. And as it happens, when we use a mole of anything, its mass will correspond to the mass given on the periodic table of elements. And so a mole of hydrogen would weigh 1.00 grams, whereas a mole of nitrogen would weigh 14.007 grams. More on that later on. For now, you need to get comfortable with two concepts. A mole represents 6.022 times 10 to the 23, and when we write balanced chemical reaction equations, in most cases, the coefficients that we write in front of the molecular formulas or the formula units represent the number of moles. The stoichiometric ratio is the same as the molar ratio. That is all for now, and I will see you on the flip side.